So today we're looking at properties of the definite integral, and in particular we want to examine what to do when we've got sections of graph that lie below the x-axis. So when a function has any negative values at all and it dips below the x-axis, the definite integral is going to have a negative value. Now why does this happen? Well, so far we've seen that our definite integral, which we know has notation like this, from a lower to an upper bound of some function, we know that we can, oh, that you can't quite see that. We know that we can use this definite integral to find the area of a section, but it's not in itself an area. All it really is a sum of values that will be equal to the size of an area. So we know it's a sum because we've got this S symbol here that's stretched out to remind us. And so far we also know that the way we get it is notionally we've got an infinite number of tiny little rectangles sitting in any space. And if we sum, there's our sum, if we add up this and sum the total size of each rectangle, then we'll get our definite integral. And the dx has come from a small change in x. That's the width of the rectangles, isn't it? And f of x is actually the height of each rectangle. And that's where this notation came from. So when we started with questions like this, here we're looking at the area underneath y equals x squared from the bounds of 0 to 2. So it's written like this. We know how to do it. We integrate our x squared, or find its primitive. We have x cubed over 3. We put it in the square brackets. We write the upper and lower bounds. And then we substitute in the upper bound first. And then we subtract the substitution with the lower bound second, and then we can evaluate it. And here we can see that this is 8/3, or 2 2/3. Now this is just a value. So if we're asked to evaluate this definite integral, the answer is 8/3. But if we're asked to find the area between the curve, the x-axis, x equals 0 and x equals 2, well then we'd say the area is 8/3 units squared. So a really important distinction to make. If you're asked for area, you use your definite integral to make a reasonable assumption about the size of the space and you put units squared on it. If you're just asked to evaluate the integral, you just leave your answer as an actual number. Now, what's happening over here? We've got y equals minus x squared, which is an upside down parabola. We know that it's identical to this one in shape, it's just flipped upside down. So when we're asked to find the definite integral between 0 and 2 of this one, we're being asked the same thing. We're looking at the size of this space between 0 and 2, x equals 2, and the curve and the x-axis. But now, when we find the sum of all of these rectangles, their heights are all negative. Now, I can hear you thinking, lengths can't be negative. No, but f of x can. And that's really what we're multiplying by the width of our rectangles. So when we go through and just perform the procedure we've already learnt on this function, negative x squared, we get the exact same value as over here, which makes sense because this is the same sized space, isn't it? But we get a negative out the front. And at first this seems counterintuitive because we think, how can an area be negative? Well, it can't, but a definite integral can. And that's the important lesson here today. A definite integral is just a value, and it can be negative. You can then be asked a secondary question, what is the area of this space? And in which case you'd look at this and you'd say, well, I've got negative 8/3, but of course an area can't be negative. So if I answer the question, what's the size of this area? I would say 8/3 units squared. I'd use the outcome of this information here that I've got to reason what the area is. Okay, so now that we can see that there's two types of questions that we can be asked, let's have a look at an example. And this example is going to take things right back. We're not even going to calculate the definite integrals using our integration techniques. We're literally going to just look at the size of some spaces that we've been given. Now here we've got y equals f of x, and you can see that it dips below the x-axis a few times. So we've been told how large these sections are in area. We've got 10 units squared, 6 units squared, 11 units squared. And the purposes of this question, and in fact we get questions like this in the HSC all the time, they ask you this just to check if you really understand what a definite integral is and how you use it to find areas. So the first type of question just says calculate the definite integral from A all the way up to B. So you say, all right, this section is 10. This section is 11. Not 10 units squared and 11 units squared, it's just 10 and 11 because a definite integral doesn't have units, it just has a value as a number. So we've got 10, we've got 11, and this one down here, if it's got an area of 6 units squared, we know that 6 must be involved, but it's also below the x-axis. And we've seen that if it sits below the x-axis, it's going to have a negative value because all of the heights are negative. So in fact, this section here has a value of negative 6. So if we're going to add up 10, 11 and negative 6, what we get is 21 minus 6, which is 15. That's the size of the definite integral from here to here. But is that the same as the area? Not quite. If we're asked to calculate the area between y equals f of x and the x-axis, between x equals a and x equals b, now we want areas, so we need them to be positive. So all we do here is say we've got 10 units squared plus 6 units squared plus 11 units squared. So we have 10 plus 11 plus 6, which gives us 27 units squared. A nice simple arithmetic problem. And this looks so simple that you might say, why is this year 12 maths? But this is a really important distinction to make. Now some terminology that you might see in textbooks. When you're performing this operation, they sometimes call this the sum of signed areas. What does that mean? Well, it means that we've attributed a special sign to each one of these areas based on whether they were positive or negative. So that if we know the area, but we're calculating the integral, we need to take this into account by adding the signed areas, rather than just adding up the areas as they